Welcome dear students. Today we are going to discuss Raman spectroscopy. So in Raman spectroscopy, it is very much similar to IR spectroscopy, but in Raman spectroscopy we use a laser light source to irradiate a sample, right? Now IR bands arise due to the change in the dipole moment of a molecule that we have already discussed on interaction of light with the molecules, whereas Raman bands arise due to a change in the polarizability of the molecule on the same interaction. So what are the two basic differences that we can observe here? That in case of IR spectroscopy we use the ordinary light, right, whereas in fact the absorption occurs from the IR region, but in case of Raman spectroscopy we use the laser light source to irradiate the sample. And the another major difference is that IR bands arise due to the change in dipole moment of the molecule, while Raman bands arise due to the change in polarizability of the molecule. Now let us talk about Raman scattering, right? So here you can see that in this diagram you can see that this is the sample molecule, this is the incident laser light, this is E0 which shows incident laser light. Now the light gets scattered, right? So here we are talking about scattering of light. So here you can see that this the energy of this scattered light is same as the incident laser light, and then there are some deflections, or you can see that there are certain shifts. So what we can observe here is that when light is scattered by matter, almost all the scattering is an elastic process which is known as Rayleigh scattering. So this is Rayleigh scattering, right? So let me show you. This is the Rayleigh scattering where E is equal to E0, right? E0 is the incident light. Now this E is equals to E0, that is the scattering occurs without any absorption or emission of light. So scattered light has energy same as the incident laser light, right? So this is known as elastic process and also known as Rayleigh scattering, that there is no change in energy. However, a very small percentage of scattering is an inelastic process. That is, the scattered light has different energy from the incident light. Again, let us consider this diagram, right? So let us see this diagram. Here you can see that E is greater than E0 and E is less than E0. So this is Raman scattered light, this is Raman scattered light. So this is not Rayleigh scattering. Rayleigh scattering is this, and the deflection in light occurs either E is greater than E0 or E is less than E0. So both the cases, both the deflections or both the shifts are known as Raman scattered lights or Raman scattering, right? So this is inelastic scattering of light, and this was first observed experimentally by Chandrasekhara Venkataraman or C.V. Raman in 1928, and therefore this inelastic scattering is also known as Raman scattering. So C.V. Raman ने इसकी discovery की थी. It was first experimentally observed by C.V. Raman, and that is why it is known as Raman scattering. So today and in this slide we have discussed what is Raman scattering. So this shift is also known as Raman effect, right? So let us talk about Raman effect now. So photons of the laser light are absorbed by the sample and then re-emitted, right? So this is known as scattering. So frequency of the re-emitted photons is shifted up or below, up or down in comparison with the original monochromatic frequency, which is called the Raman effect. So पिछले डायग्राम में हमने क्या देखा कि if E is greater than E0 or E is less than E0, right, either the energy is absorbed by the molecule or energy is re-emitted, right? So in that way energy is either less than E0 or greater than E0. Then these shifts are known as Raman shifts, or this effect is known as Raman effect. So Raman spectroscopy can be defined as a spectroscopic technique based on inelastic scattering of monochromatic light, usually from a laser source in the near ultraviolet, visible and near infrared range, right? So the absorption occurs in the near UV, visible and near IR region. So this is how we can define the Raman effect. So Raman effect is actually defining the Raman scattering, and Raman scattering is it is beyond the Rayleigh scattering, and it is very small part of the entire process, entire scattering process. So almost all the radiations are scattered as such. So all the light is scattered as such. So it is known as elastic scattering, and that is also known as Rayleigh scattering. But some part is deflected, or you can say that energy or frequency goes up or down, then it is known as Raman scattering, and the effect is known as Raman effect. Now let us define Raman scattering. Types of Raman scattering. So scattering may be of two types. It may be classified into two types. First is Stokes-Raman scattering. So let us know what is this Stokes-Raman scattering. Stokes-Raman scattering is a process in which an electron is excited from the ground level and falls to a vibrational level. Right? So here you can see that this is the first of all, let us consider Rayleigh scattering. So here you can see that electron is there present at the ground level. It jumps from the ground level to the higher virtual energy states, higher level, and then it comes back to the ground level. So there is no change in energy. So this is Rayleigh scattering, as we have discussed earlier. Now when we are talking about Stokes-Raman scattering, so here you can see the electron is present in the ground level. Now from ground level it jumps to the higher virtual energy state, and then it falls back to any of the vibrational levels. So in that way, here you can see that some of the energy is absorbed, right? So it involves energy absorption by the molecule. तो जब molecule यानी substance के through energy absorption हो जाएगा, तो जो scattered light है उसकी energy कम होगी, right? So thus Stokes-Raman scattering light has less energy than the incident light. So when we were talking about that E is less than E0, it was Stokes-Raman scattering. Now what is anti-Stokes-Raman scattering? Anti-Stokes-Raman scattering is a process in which an electron is excited from the vibrational level to the ground level. Now here you can see that electron is excited from the vibrational level. It is not present in the ground state, but it is present at the vibrational level, right? And then it gets excited to the higher virtual energy states and then returns back to the ground level. So in that way the energy is emitted, right? So energy is scattered. So here you can see that it involves an energy transfer to the scattered photon, and thus anti-Stokes-Raman scattered light has more energy than the incident light. So earlier we were discussing about under the Raman effect that there is either E is less than 0 or then E is greater than 0. So here E is greater than E0. So intensity, or you can say the energy or the frequency of scattered light is greater than the intensity or frequency of the incident laser light, and therefore this is known as anti-Stokes-Raman scattering. So I hope it is clear to everyone that there are two types of Raman scattering. One is Stokes and the other is anti-Stokes. So anti-Stokes, Stokes means E is less than E0, and anti-Stokes means E is greater than E0. Right, so types of Raman scattering when we are discussing, then we must understand that Raman scattering is an extremely weak process, as we have discussed that there is a very small portion of the scattered light which represents the Raman scattering. Almost all the scattered light is the Rayleigh scattering, or you can say that elastic scattering. So Raman scattering is an extremely weak process, and only one in every 10 to the power 6 to 10 to the power 8 photons scatters, right? So in standard Raman scattering measurement, what we do, Rayleigh scattered light is rejected, जिसका बहुत ज़्यादा जो पूरी तरह से scattered हो जाता है बिना किसी change energy change के, उसको हम लोग किसी filter के through उसको eliminate कर देते हैं, and only the Stokes-Raman scattering is recorded for simplicity. और anti-Stokes भी की energy या frequency कम होती है, इसलिए जो major हमारे लिए important जो scattering होती है, scattering वाला part होता है, वो कौन सा होता है? Stokes-Raman scattering. Right? So this is how you can see that this is the Stokes band, this is the Rayleigh band, and this is the anti-Stokes band. Right? So the intensity is high. In case of Stokes band, intensity is high, and then in case of anti-Stokes band, you can see that intensity is less. So here you can see that this is how Raman effect occurs. Now another important topic related to Raman scattering is selection rule. So let us consider a diatomic molecule which may be regarded as a rigid rotor. Now what is rigid rotor? It is a rigid dumbbell joined along its line of center by a bond equal to bond distance r between the two nuclei. Suppose there are two atoms, right, and they are joined by a bond, and the bond the length is equal to bond distance r, right? So they are joined through two nuclei. So this is also known as or considered as rigid rotor. Now if we consider a rigid diatomic rotor, so here we can see that delta J is equal to plus minus 1. So what is J? J is the rotational quantum number. So delta J is equals to plus minus 1. That is the value of J, that is rotational quantum number, changes only by 1 unit, right? So plus minus 1 means the plus sign indicates absorption and minus sign indicates emission of radiation. And the transition occurs only from j is equals to 0 to j is equals to 1, or j is equals to 1 to j is equals to 2, or j is equals to 2 to j is equals to 3, and so on. But it cannot happen like this, like j is equals to 0 to j is equals to 2, or j is equals to 1 to j is equals to 3, etc. Because here you can see that delta j is equals to plus minus 1. So there is a change of 1 unit only, right? So these j is equals to 0 to j is equals to 2, or j is equals to 1 to j is equals to 3, these are forbidden transitions, right? So hence we can see that j can only be 1 unit higher than j dash, so j minus j dash is equals to 1. So let us consider this further explanation. So the allowed energies of a rotating diatomic molecule can be expressed as E is equal to B is constant, J plus 1. Right, so J to J plus 1. So the transition occurs from J to J plus 1 and so on. So E is equals to B J plus 1 centimeter minus 1, where B is equals to constant. So E is equals to B J plus 1. So let us consider that there is a transition from J to J plus 1. So we will consider the energy change E j plus 1 minus j. So E j plus 1 is equals to B. We have to consider this formula B. So j is j plus 1 and j plus 1 plus 1. So in that way, minus B Ej means j plus 1, right? So Ej means j plus 1 and Ej plus 1 we have considered here. So when we open this equation, then we get delta E j to j plus 1 is equals to 2B j plus 1, right? So this you can consider delta E. Delta E is equal to 2B j plus 1. So this is E, right? But this is delta E. So when we are considering the transition from j to j plus 1, so it comes out to be delta E is equals to 2B j plus 1, right? So let us move ahead. So here you can get a clear idea, right? So this is one level, this is another level, this is another level. So here you can see if this level has energy j is equals to 0, rotational quantum number j is equals to 0, j is equals to 1, 2 and 3 and so on. So if electron jumps from here to here or from here to here, so only these are for allowed transitions, but not from j is equals to 0 to j is equals to 0. It is not allowed. So these are known as forbidden transitions. So if we are considering delta E is equals to delta E j to j plus 1 is equals to 2B j plus 1, we have already determined this formula. So let us consider if the transition is from 0 to 1. So E 0 to 1 will be 2B, j is 0, so 0 plus 1, right? So here it comes out to be 2B. Delta E is equals to 2B, 1 plus 1, then 4B, right? So here you can see that there are series of closely spaced lines separated by 2B, 4B, 6B and so on. So thus, if all transitions take place, the absorption spectrum would consist of a series of lines at 2B, 4B, 6B and so on up to 2J plus 1B centimeter minus 1, 2B J plus 1 centimeter minus 1, right? So 2B, 4B, 6B and so on. So this clearly indicates that the rotation spectrum of a diatomic molecule consists of a series of lines with frequency separation of 2B centimeter minus 1. So specific selection rule for diatomic molecule is delta J is equal to 0 plus minus 2. So plus is Stokes scattering, minus is anti-Stokes scattering and 0 is the Rayleigh scattering. So this is the specific selection rule. So whenever you have been asked about the selection rule, you can give this kind of description. So here you can see that this is the diagram which shows the Raman spectrum of CCl4, carbon tetrachloride, measured using a 532 nanometer laser. So this is an example of Raman spectra of in case of carbon tetrachloride, and here you can see that this is a tetrahedral molecule with 3 pronounced Raman active vibrational modes in the region of 100 to 500 centimeter minus 1, right? So here you can see these 3 active or pronounced Raman, Raman active vibrational modes are present here. These are Raman active vibrational modes, right? So these active or pronounced Raman active vibrational modes are present from 100 to 500 centimeter minus 1. So these Stokes lines are considered. These Stokes vibration modes are considered, right? So there is an additional peak at 780 centimeter minus 1, which is not shown here. So here this is the explanation. In the center of the spectrum is the Rayleigh scatter peak at the laser wavelength. This peak is millions of times more intense than the Raman scatter, but इसको हम neglect करते हैं. जैसा हमने बोला था कि Rayleigh scattering को हम लोग neglect कर देते हैं. how we use a notch or edge filter in the Raman spectrometer, was included here for clarity. इसको हम clarity के लिए हमने यहाँ पर रखा हुआ है, लेकिन इसको हम लोग कंसिडर नहीं करते हैं. वी निगलेक्ट दिस रेले स्कैटरिंग, बट क्लैरिटी के लिए इस डायग्राम को यहाँ पर शो किया गया है. सो रेले स्कैटरिंग बहुत इंटेंस होता है और इसको हम लोगों ने यहाँ पर निगलेक्ट करेंगे, तो ये हमको केवल प्रोमिनेंट दिखेगा स्टोक्स रामन स्कैटरिंग. So symmetrically placed on either side of the Rayleigh peak are the 3 Stokes and 3 anti-Stokes peaks corresponding to the 3 most intense Raman active vibrations of CCl4. So on either sides, here you can see Stokes and here you can see anti-Stokes Raman scattering. It can be seen that the anti-Stokes lines are much weaker than the Stokes due to the larger population of molecules in the ground vibrational levels of each mode. Right? So यहाँ पर आप देख रहे हैं Stokes की intensity anti-Stokes की comparison में बहुत ज़्यादा है, क्योंकि जितने भी वाइब्रेशंस होते हैं वो ग्राउंड लेवल से हायर वर्चुअल स्टेट्स में जाकर और फिर वाइब्रेशन लेवल में आके होते हैं. सो स्टोक्स रामन स्कैटरिंग की इंटेंसिटी ज़्यादा होती है. CCl4 has one of the simplest Raman spectra, but the same principle applies for all samples. Raman spectroscopy is used to measure the unique vibrational fingerprint of the sample, and from that information, chemical structure and physical properties can be determined. So what is the conclusion? That we can determine the structural features and physical properties of different molecules with the help of Raman spectroscopy. So let us consider the applications of Raman spectroscopy. So Raman spectroscopy is superior to IR spectroscopy. First of all, we must remember this for investigating inorganic species, because aqueous solutions can be employed. राइट. तो इसमें एक इम्पॉर्टेंट बात आप याद रख सकते हैं कि रमन स्पेक्ट्रोस्कोपी में हम एक्वस सोल्यूशन एम्प्लॉय कर सकते हैं, यूज़ कर सकते हैं. द वाइब्रेशनल एनर्जीज ऑफ मेटल लिगेंड बॉन्ड्स आर जनरली इन द रेंज ऑफ 100 to 700 cm-1, and this is a region of the infrared that is difficult to study. So these vibrations are frequently Raman active. So this is the application of Raman spectroscopy. इसके अलावा हम देखते हैं कि Raman studies are potentially useful sources of information concerning the composition, structure and stability of coordination compounds. So जिस तरह से इनऑर्गेनिक स्पीशीज़ की स्ट्रक्चर डिटरमाइन करने के लिए, उसके इन्वेस्टिगेशन के लिए रमन स्पेक्ट्रोस्कोपी हेल्पफुल होती है, बिल्कुल उसी तरह कोऑर्डिनेशन कंपाउंड्स के कॉम्पोजिशन, स्ट्रक्चर और स्टेबिलिटी को डिटरमाइन करने में, उसकी इन्फॉर्मेशन लेने में रमन स्टडीज़ बहुत इंपॉर्टेंट होती हैं. रमन स्पेक्ट्रोस्कोपी हैज़ बीन अप्लाइड वाइडली फॉर द स्टडी ऑफ बायोलॉजिकल सिस्टम्स. क्वांटिटेटिव एप्लीकेशंस अगर हम देखें तो इसके कुछ एडवांटेजेस भी हो सकते हैं और डिसएडवांटेजेस भी हो सकते हैं. Raman spectra tend to be less cluttered with peaks than infrared spectra. As a consequence, peak overlap in mixtures is less likely. अभी अगर हम Raman spectra की बात करेंगे तो जो उनके peaks होते हैं वो बहुत ज़्यादा cluttered नहीं होते, जिसकी वजह से जो ये इनकी mixing नहीं हो पाती है, और consequently क्या होता है, इसकी quantitative measurement बहुत simple हो जाता है. So this is the advantage. इसके अलावा Raman sampling devices are not subject to attack by moisture and small amounts of water in a sample do not interfere. जैसे कि हम लोगों ने अभी डिस्कशन किया कि Raman स्पेक्ट्रोस्कोपी में एक्वस सॉल्यूशंस का भी यूज़ होता है, और उसके अलावा जो सैम्पलिंग डिवाइसेस हैं उन पर मॉइस्चर का अगर अटैक होता है तो जो भी वाटर है, मॉइस्चर है, और वो सैम्पल के स्ट्रक्चरल फीचर्स को डिटरमाइन करने में कोई इंटरफेरेंस क्रिएट नहीं करता है. डिसएडवांटेजेस क्या हो सकते हैं? इन एडवांटेजेस के अलावा रामन स्पेक्ट्रोस्कोपी हैज़ नॉट येट बीन एक्सप्लॉइटेड वाइडली फॉर क्वांटिटेटिव एनालिसिस. यानी इतनी एडवांटेजेस या कैरेक्टरिस्टिक फीचर्स होने के बावजूद इनका हम अभी बहुत ज़्यादा वाइड एप्लीकेशन क्वांटिटेटिव एनालिसिस में नहीं करते हैं. दिस लैक ऑफ यूज़ हैज़ बीन ड्यू लार्जली टू द rather हाई कॉस्ट ऑफ रामन स्पेक्ट्रोमीटर्स रिलेटिव टू दैट ऑफ एब्जॉर्प्शन इंस्ट्रूमेंटेशन. तो कॉस्टली अफेयर होने के कारण भी इसका यूज़ कम होता है. तो एक बार हम फिर से देख लेते हैं कि रामन और आईआर स्पेक्ट्रोस्कोपी को कैसे हम कंपेयर कर सकते हैं. जैसे हम लोग ने पहले कहा था कि रामन और इंफ्रारेड स्पेक्ट्रा काफ़ी सिमिलर होते हैं, राइट. उनके रीजन्स जो हैं फंक्शनल डिटेक्शन के लिए और फंक्शनल फिंगरप्रिंट रीजन की तरह ही बिल्कुल ऐसे यहाँ पर भी यूज़फुल इन्फॉर्मेशन हमें मिलती हैं, राइट. इनफैक्ट रामन स्पेक्ट्रा से काफ़ी ज़्यादा इन्फॉर्मेशन हमें मिलती है ऑर्गेनिक कंपाउंड्स की और इसके अलावा इनऑर्गेनिक कंपाउंड्स के लिए. बट हियर यू कैन सी दैट रामन की कुछ स्पेसिफिक फीचर्स भी होते हैं, जैसे वाटर इज़ अ वेरी वीक रामन स्कैटरर, राइट. तो रामन स्पेक्ट्रा में जो हम सैम्पल्स ले रहे हैं वो एक्वस सोल्यूशन भी ले सकते हैं, एंड हाइग्रोस्कोपिक एयर सेंसिटिव कंपाउंड्स कैन बी ऑब्टेन्ड विदाउट मेजर इंटरफेरेंस फ्रॉम वाटर वाइब्रेशंस एंड इट्स रोटेशन फाइन स्ट्रक्चर्स दैट आर एक्सट्रीमली स्ट्रॉन्ग इन IR एब्जॉर्प्शन स्पेक्ट्रा. सो IR एब्जॉर्प्शन स्पेक्ट्रा में ना तो हम एक्वा सोल्यूशन का यूज़ कर पाते हैं, या फिर हम देखते हैं कि मेजर इंटरफेरेंस आता है वाटर के कारण, मॉइस्चर के कारण, जो कि रामन स्पेक्ट्रोस्कोपी में नहीं होता। इसके अलावा हम देखते हैं कि आईआर स्पेक्ट्रोस्कोपी में अगर हम ग्लास का यूज़ करते हैं तो वो इंटरफेरेंस क्रिएट करता है, राइट। इन आईआर टेक्निक इट इज़ इम्पॉसिबल टू यूज़ ग्लास एज इट एब्जॉर्ब्स आईआर रेडिएशन। तो ग्लास भी आईआर रेडिएशन को एब्जॉर्ब करने लगता है, लेकिन यहाँ पर ये इंटरफेरेंस क्रिएट नहीं करता है। रामन एक्सपेरिमेंट यूजेज अ लेजर बीम ऑफ अ वेरी स्मॉल डायमीटर, thus a very small quantity of the sample is needed to be characterized, right. So यहाँ पर लेज़र लाइट का यूज़ कर रहे हैं instead of IR light or ordinary light, and therefore the small quantity of sample can be characterized. Laser source used by Raman needs to be carefully dealt with, so it could cause local heating up for the sample, burn the sample, or cause it to decompose. So careful dealing is very much required. Raman instruments need careful calibration as they record the shift in frequencies, unlike the IR technique. तो यहाँ पर चूँकि हम लोग शिफ्ट ऑब्जर्व करते हैं, तो रामन स्पेक्ट्रोस्कोपी में कैलिब्रेशन बहुत इंपॉर्टेंट है। रामन स्पेक्ट्रोस्कोपी इंफ्रारेड स्पेक्ट्रोस्कोपी या आईआर स्पेक्ट्रोस्कोपी से सुपीरियर भी मानी जाती है अगर हम इनऑर्गेनिक सिस्टम्स की बात करें, क्योंकि यहाँ पर एक्वा सोल्यूशन भी हम लोग यूज़ कर रहे थे, जो हम लोगों ने पहले भी डिस्कस किया था। Raman studies are potentially useful sources of information concerning the composition, structure, and stability of organic compounds. So these are certain applications which are going to be repeated. So I'm not going to repeat here. So let us summarize today's lecture. So Raman spectra rise due to scattering of light by absorbing molecule. So here you can see that there is a sample molecule and there is an incident laser light and there is scattering of light. So it involves scattering of light. Exactly when the light is absorbed, so energy of the scattered light may be less or high. So Raman spectra can be obtained even for simple molecules such as oxygen, N2, C2, etc. यानी डायटोमिक मॉलिक्यूल की अगर हम बात करेंगे तो रामन स्पेक्ट्रा बहुत यूज़फुल हो सकते हैं, जिनमें अगर हम डायटोमिक मॉलिक्यूल की बात करें जिनमें डायपोल मोमेंट में चेंज नहीं होता है, क्योंकि आईआर स्पेक्ट्रोस्कोपी से हम ऐसे कंपाउंड जैसे मॉलिक्यूल्स के स्ट्रक्चरल फीचर्स को हम आइडेंटिफाई कर पा रहे हैं जिनमें देयर इज़ अ परमानेंट चेंज ऑफ डायपोल मोमेंट। बट यहाँ पर डायपोल मोमेंट नहीं बल्कि पोलराइजेबिलिटी की बात होती है, तो यहाँ पर ये इंपॉर्टेंट डिफरेंस हम लोगों ने डिस्कस किया। सो सच अ स्टडी हैज़ नॉट बीन पॉसिबल बाय आईआर स्पेक्ट्रोस्कोपी, सो इट इज़ वेरी यूजफुल दैट वी कैन एम्प्लॉय रामन स्पेक्ट्रोस्कोपी. It is a non-destructive technique, right? So the measured sample can be reused for other purposes afterwards. So this advantage, or you can say that this characteristic of spectroscopy, Raman spectroscopy, is not only for Raman spectroscopy but for all spectroscopic techniques, that the spectroscopic technique is a non-destructive technique, and similarly Raman spectroscopy is also a non-destructive technique, that is the entire amount of sample can be recovered. Analysis is quick, as similar to all the spectroscopic techniques. It is faster than most of the other methods, and that is why it is very much useful in identifying the structures of the compounds. And the technique is suitable for aqueous solutions. So Raman spectroscopy does not suffer from strong absorbance of water, which is a common problem for IR spectroscopy, right? So this is all about Raman spectroscopy. So in this lecture we have given a very basic idea. We have talked about the basic idea of Raman spectroscopy. We are not going to discuss in detail, because in a BTech syllabus, especially when we talk about the engineering first year chemistry, you must understand that what is the basic difference between IR spectroscopy and Raman spectroscopy, and what is actually the basic principle of Raman spectroscopy. Besides, selection rule is also very important. Thank you very much.